Welcome to MRU E-Learning powered by Malla Reddy University. AI is on trend now, but do you know when was the first research article of AI was published? It happened in the year 1943. The concept behind the paper was building a mathematical model on a human brain. So, an artificial neuron. Myself, Dr. G. Gifta Jarith, Dean of AML Department, School of Engineering, Malla Reddy University. So here we are going to see about the basic building block of artificial intelligence. The basic building blocks of artificial intelligence are data, algorithms, search techniques, infrastructure, and various machine learning models. So we are going to see about the search techniques which makes the artificial intelligence, takes the artificial intelligence to the next level. So what is this artificial intelligence? Artificial intelligence is a simulation of a human brain. That is, if there is something artificial, then we can tell that something is natural too. So what is that natural? The humans have the natural intelligence, which were tried to be made into the machines. So the machines has to be programmed to think, learn, and perform various tasks. What kind of tasks we expect the machines to do? The artificial intelligence deals with the various tasks like reasoning, perception, understanding various languages, learning from the existing things to solve certain problems, and finally the very important thing is decision making. Because we can tell that the basic thing that we can find in this world is data. When it comes to data, they are all very raw. For example, if I tell Malla Reddy University, this is a part of data, a raw data. And I can tell that Hyderabad, this is another data. So when we combine these data together, we will get some information. Malla Reddy University is a state private university in Hyderabad. So here we are getting some information. The next level of information is knowledge. Knowledge comes when we gather a set of information. And the fourth level of this is intelligence, which means the decisions has to be made on the basis of situations, on the basis of circumstances. The system should adapt to the new environment. Only then we can tell that it is intelligence. So in order to make the human intelligence, simulate it into a machine, we can call it as artificial intelligence. So it uses a lot of algorithms. What is an algorithm? The set of actions that is being needed for the development or to solve any problem. So the algorithms will define a set of functions which can mimic the human cognitive functions. What are the various applications of such algorithms? So we have seen that algorithms are a set of steps which can solve a problem. And what is this search algorithm and how the search algorithm is related to the artificial intelligence? When we make some decisions, how the human usually makes the decisions, we will have multiple options in front of us and we will try to find the best among them. For example, if we are planning to go for a movie tonight and every family members are getting ready, it is time to leave the home. One of the family member is getting a call from some friend that there is an accident for his father. That particular guy, the child of that family, immediately withdraws the plan and plans to go to the hospital. So according to the situations, if the decisions are made, so in order to make these decisions, we need to follow some steps. So the searching of the solution, we call them as search algorithms. Where do we use these search algorithms? In the development of AI. The first application is a navigation system. We all use Google Maps. Even in Google Maps, it will show a lot of paths to us, different ways to reach the destination. But we will choose one among them, and that also will be suggested by the system to us. So here we can see an example that from the source towards the destination, towards the terminal, we have 5 different paths and we can choose one among that. So how these paths are being made, we can find some points over there. These points are connected by means of a search algorithm. Another important application of AI search algorithm is playing games. So in this window, we can see some of the games: Connect 4, Sudoku, Tic-Tac-Toe, Number Puzzle, AlphaGo, as well as the chess. So all these games, nowadays the humans are playing against the machines, and we know that the machines will win. So how this happens? And even in the real world, we can see that the people are playing rummy, some betting games against the computers. It seems that the human is winning in the beginning, but later on, the system will learn about the strategy the human uses, and accordingly, the human will fail and human will be in the loss. AI always wins. So here also we can see that in the year 1996, the company IBM, they have developed an application called Deep Blue, and that application won the world champion Gary in the year 1996. Similarly, another application named AlphaGo, which played Go against Fan Hui, it beat Fan Hui in the year 2015. So these are a major application of the search algorithms in gaming. And the last application of search algorithm is helping in making decisions. The very important thing that we expect from a search, from an artificial intelligence system is decision making. So these search algorithms will support in making decisions, because when we try to solve a problem, in this graph we can find that we are getting multiple ups and as well as multiple downs. So we have to select the best point among this. A single problem will have multiple solutions. So the algorithm should try to find out the best solution among all the solutions. So these search algorithms will support us a lot to select the best solution. So these are various applications of search algorithms. And what is the significance of the search algorithm? So how they provide solutions and how they support in artificial intelligence. The first thing is it will solve the artificial intelligence related issues. So artificial intelligence, in the sense we can mean that this human intelligence is being mimicked. When looking at this, we can see that human intelligence always, it is good in making decisions. So one of the best thing is it can solve all AI related issues. And it will help in the resolution of search issues. When a search is being made, there comes certain things named search space, start, as well as goal state. That is, when we are trying to solve a problem, initially we will be in some state. So that we can call it as the start state. And our expectation is to reach some solution. So that is our goal state. So moving from the start to goal, we'll go with different paths. So every step, the algorithms will support us. And another important significance is in the case of AI agents. AI agents are small models where we can sense the elements, some operations will be performed inside, and then it will give us some results. So this perception of data happens in the AI agents, and search algorithms plays main role in this AI agent developments. And the final thing is it will help us in solving the problems and to find the best possible solution. Even though there is a solution, there will be more than one solution, and we should be capable of finding the best solution. So that best solution will also be supported by means of the search techniques. These are various significance of using the search techniques. So before moving into the search algorithms, we should know what are the basic terms that comes along with these search algorithms, the terminologies that comes in the search algorithms. The first thing is when we move into search, as we discussed in the previous slide, we can say that search space, start state and goal state are very important. Here in this diagram, we can find out a 8 puzzle board. It is a 3x3 matrix board and 9 columns are there and 1 column is left free, and we can find that number 9 is not there from 1 to 9. The numbers from 1 to 8 are there. Our expectation is to bring this initial board. This is the initial state. We can tell that this is the initial state. So this has to be turned up by step, and we have to make it into this goal state. This is our goal state. So how we can move this? Here we can see that the empty column is in the middle. So there are 4 different possibilities. The first possibility is we can move 2 downwards. The first possibility is we can move 2 downwards. So here we are getting that solution. The 2 is being moved downwards and this column is left free. And the second possibility is 4 can be moved to the left. So here we are getting the second option. 4 is being moved to the left. So we are moving 2 here. If 4 is being moved, we are getting this. And the third thing is we can move 6 towards up. So we are getting this third solution. And the fourth solution, we are getting that 8 can be moved to the right. So there are 4 different actions here, left, right, up or down. 4 different movements happens. So any one of the movement will try to bring it towards this goal state. So if it reaches to the goal state, we can stop the search. Search is over. If not, we have to try again. So in every state transformation from the initial state to the next state, in every state transformation, we have to check whether we have reached the goal state or not. If we haven't reached, again, we can move for more additional stages. So again, we can see, for example, here, if we see this space is left free. So 3 different movements are possible. 3 can be moved, 4 can be moved, as well as 5 can be moved. So if we move 4, we are moving back to the previous state. So we will avoid it. So instead of that, we can have 2 different movements. 3 can be moved down and 5 can be moved up. So we are getting these 2 states here. So from every state, when we perform an action, we are going to another state. And that state, we should check whether it is the goal state or not. If not, we can move to further more and more movements. So why artificial intelligence is needed here? The thing is, we will get different kinds of solutions here. This path may lead us to some solution in some depth. And this may lead us to some solution in some depth. But we have to find that which is the best one, in which movement we got the solution easier. So when the machine learns this repeatedly, automatically, when the human is playing against it, it will guess that what will be the human's next move. It will learn from the human's movements. Okay, so these are the search techniques. Some more search techniques are there. It is a search tree. The search tree is the one in which the previous slide we have seen. We'll get a tree structure. We'll start from an initial node. From there, we'll get child, child, and child. Until some leaf nodes, we can move on. Actions. So I have mentioned that 4 different actions can be performed in that 8 puzzle problem. Up, down, left, and right. So we can go with any actions. Each action will take us from one state to another state. That transition, we call it as a transition model. Transition from one state to another state, it depends upon the action which we do. And path cost, the total cost which takes us from the initial state to the solution state is called as the path cost. This cost varies for different paths. Solution. So when we take some actions, the sequence of actions takes us from start node to the goal node. This sequence of actions, we call them as solution. And I mentioned that there will not be a single solution. There will be multiple solutions for every problem. So among all the solutions, we should try to find the optimal solution. How can we try it? We can use the pathcast for the finding of optimal solution. We can use the timing, what time it takes for the execution of that, and how long it takes to reach the solution. So all these terms can be used for finding out which is the optimal solution. 4 different properties are there for a search algorithm. Why these properties are being used? First, let me introduce that to you. Because we have to find the optimal solution. So how to find the optimal solution? Some parameters should be there. If we are going to purchase some cloth material from a shop, we will compare the cost, we will compare the quality. So some parameters we are keeping. So in the same way, in order to find out the best solution, among the set of solutions, we are using these parameters. First parameter is completeness. So what is completeness? If the algorithm gives you a solution At least one solution. It should be there. Then we can tell that it is complete. If it is not giving, it is incomplete. That algorithm cannot be relied on. Second one, optimality. Many solutions should be there and your algorithm should provide a best optimal solution. So that is your optimality. The third thing is time complexity, and fourth is space complexity. Complexity is a very large area in the case of algorithms. This will measure you how much memory is needed for space complexity and how much time is needed for the execution of the algorithm. This will have best case, average case, as well as worst case. And in most of the cases, we will consider at least in the worst case, we should get the best algorithm. And regarding the types of search algorithms, two different types of search algorithms are there: uninformed and informed. So uninformed in the sense, no additional informations are there. We can also call it as a blind search. Holding our eyes closed, we are looking for a search algorithm. Then it is uninformed or blind search algorithms. In the other hand, we can have informed or heuristic algorithms, because we will have some additional information about the solutions. Then we are moving step by step towards the solution using this additional information. Then we call it as heuristic search or informed search. An example I can let you know. Suppose we are in the bank of a river. We have to cross the river. We have to reach the other bank of the river. And the water flow is little low. There are some stepping stones. We can find that stones are there. So if we move towards the next stone, we are not looking at the destination point. Just we are looking at the next stone I have here. I am stepping on that. There are multiple stones. Among that, I am stepping to the first one, any one of that. From there, I am trying to find whether the next stepping stone is there or not. I am going to the next. So this is uninformed. I don't know whether I'm moving towards the path of the destination. I may move in the other direction also. In the other hand, I'm looking at the destination. Someone from there is guiding me. Yeah, you can step into the stone. And I know that I'm moving in the correct path. I have some information. No, don't step over there. That stone is slippery. If the person is giving me information, some additional information I have regarding the destination, then that is called as informed search. So there are different types of uninformed searches: breadth first search, depth first search, uniform cost search, iterative deepening depth first search, and bidirectional search. So among these, here we will be discussing about breadth first search and depth first search. These two algorithms we are going to solve in this session. And in the heuristic search algorithms, we do have greedy best first search, hill climbing algorithms, A-star search algorithms. A-star can be implemented using tree concept as well as graph concept, because if it is tree concept, less memory will be consumed. We will not be saving about the past histories. If it is graph, past history will be saved and it will give you a best solution also. And weighted A-star graph algorithm. So among these, today we will be seeing about the greedy best first search as well as A-star search algorithms. So these four algorithms we will be solving today in a same graph, so that we can have a comparative study on the informed and uninformed search algorithms. We'll see how its properties are working and how it is supporting the search techniques. What are the prerequisites needed to understand these search algorithms? We should have some basic idea on various data structures, some abstract data types too. The first one is a tree. Here you can find a tree structure. So A is called as the root node. So this is called as the root node, and A is having two children. A have B and C. So B is a child, C is a child. B and C share the relationship of sibling relationship because they have the same parent. So again, we can tell that B's parent is A and B's children are D, E and F. Okay, so in this way the relationship goes on, level by level it goes. We call this as the depth of the tree. So A, the root node is in depth 0. These nodes are in depth 1. depth 2, depth 3. All these terms we will be using when we are solving the algorithm and when we are trying to find out the complexity of the algorithms. And these nodes which don't have children, we call them as leaf nodes. So these are the basic things about the tree. The next is about a graph. The tree don't have a backward edge towards the parent node. But in the case of a graph, we have chances to move from one direction to other as well as other direction. There are directed graphs as well as undirected graph. So in this diagram, we can see it is an undirected graph. 6 different nodes are there. We call these as nodes. These are all called as nodes. And there are lines which connect the nodes. These are called as edges. Okay, the nodes can also be called as vertices. So using this structure also we can solve a lot of problems. The third prerequisite to understand about the algorithms is a stack. A stack is a data structure where there will be only one entry and exit point, a single entry exit point. So we can tell that a pile of plates are being arranged. Usually when we go for functions, when we go for banquets, we'll have a pile of plates. We don't take the plate from the bottom. We will always take the plate from the top. And if a person keeps the plate, it will be kept on the top. So always, which is being kept last into the stack comes out first. That is, last in, first out happens. And the operation of keeping onto the stack, putting into the stack, we call it as push. And taking the data out of the stack, we call it as pop. So this data structure will be used in our algorithm. So this is the next prerequisite. The next one is a queue. We can think of a queue in a theater or for a ticket counter. So always the person who comes new will not go and stand in front of the queue. Already the queue is there, the person will be joining to the back end. We call it as the rear end. And the person who gets the ticket first is the person who stands in front of the queue. So we can tell that there is a front, there is a rear. So always data will be added to the rear part and the exit from the queue always happens in the front part. The operation for keeping the data into the queue, we call it as NQ operation. And when we take the data out of the queue, we call it as DQ operation. So this NQ and DQ are not happening in the same point. In the case of stack, both push and pop happened in the same pointer. But here, the NQ and DQ are happening in 2 different exit and entry points are there. So this data structure also we will be using. We also have a double-ended queue. That is, in both the ends, we can do any operations. That is also being applicable. We have a concept called priority queue. We'll be seeing it next. And the next data structure is a set. Just like an array, if we have to keep note of some data with us, we can use this set. We commonly use the set bracket for representing this set of data elements that we can see over here. And how it gets entered into the memory, here we can see that we are using a hash table. So using a hash table, we are entering the data into the particular locations. So why we are using this hash table is in order to receive the data easily, to access the data easily, we are using this hash table. So this is how the data is being stored inside the memory. And the last data structure, this is not a data structure actually, it is a data structure the priority queue uses the data structure queue, and it is a type of abstract data type. We call it as an abstract data type. So in the priority queue, similar to a queue, we will be having NQ and DQ operations. In this figure, we can find that NQ is happening at one end, but DQ is not happening in the other end. It is not happening here. How this happens in the priority queue? The NQ and DQ exit entry point can be anywhere in the queue. That is how the priority queue works. We will be using a priority. It may be a maximum value has to be taken out. Anywhere the maximum value is there, it will come out. So here we can see that 785 is the maximum value in the elements in the queue. So the element which has the highest priority or the minimum element can be selected, or in most of the cases when we go for priority queue, we will have a priority list. So which element has the highest priority will be kept in the DQ end. So it will be easier for us to access the data which applies some priorities. So these are various prerequisites. Let us move to the first uninformed search technique, breadth first search. So if it is breadth, already I mentioned we are going to deal with breadth first search and depth first search. Breadth in the sense it goes in this direction. Depth, it goes in this direction. So the same we are going to apply in our algorithm. So breadth first search is a graph traversal algorithm. So it is going to work on a graph, but we will make a tree out of graph for our convenience. That will explore all the neighboring nodes to that particular node which we are visiting. So in this diagram, we can see that we are having a starting node. We call it as the parent if it is a tree, but actually we are working on a graph over here. We call this as the source node. So from the source node, 3 different nodes are being connected. So we can find that the nodes 1, 2 and 3 are getting connected. We are telling this as layer 1. As I said, this is of depth 0, depth 1, depth 2 when we come across a tree structure. So here this is layer 1. Once the first layer is completed, we will move to the second layer. This is the basic structure of a breadth first search. So all the children of 0 will be visited first. Once all the children are over, if there is a 4th child, it will be visited and then we will move to the next layer. So when we go to the next layer, the first node of the first child of the parent node will be explored again. So it goes in this way. So always it will complete first layer, then it will go for the second layer. If it goes in this way, then we call it as breadth first search. And the data structure that we use in breadth first search is a queue. So how does this queue work? The queue will be having an entry point and an exit point. So this is how the queue works. And in order to find the shortest path, commonly we will be using this algorithm. This will work on both tree as well as graph. If it is a graph, it will work on both directed and undirected graphs. Where we are using this, the applications of BFS to find the shortest path. It can be used in the navigation systems. Many different shortest path algorithms are there. This is one among them. And in order to check whether a path exists between 2 nodes, because when we consider a graph, some graph points will be connected and some other points will not be connected. So if I want to check, let me name them as A, B, C and D. If I want to check whether there is a path existing between C and D, I can use this BFS and I can find that the answer is no, because when I track and find the solutions, there will be no connection between C and D. I can tell there is no link between C and D. And for crawling or searching data, crawling in the sense moving slowly from one page to another page in search of verb pages and all, we can use this BFS. And the last use for BFS is solving puzzles. When we solve the word crosswords and all, we can go for this BFS. We are going to discuss about the pseudocode and a program also in this session. So the first step is to initialize an empty queue and a visited set. So how this empty queue will be? We'll initialize a queue. Nothing will be there. There will be a front as well as rear. As nothing is there, both are in the same point now. When we add the element, the rear pointer moves towards the other direction. Front stays same. When we dequeue something, the front element goes out. And the second thing is, the starting node is enqueued. That is, the first node, we are keeping it into the queue. So if 1 is the first node, we can keep it into the queue. Now, when we are marking it as visited, it means we are exploring its children. All those elements are entered into the queue. And finally, until the queue gets emptied, one by one, we are going to take them out and explore them. So initially, 1 is being kept inside and 1 is marked as visited. So when 1 comes out, what happens? From the previous example, 2, 3 and 4. Its 3 children will get inside. So we can tell like this. So we'll have the queue. 1 will enter inside. Now into the visited set. We have a set called visited. When we dequeue the element from the queue, 1 comes over here. So when 1 is being dequeued, its children 2, 3, 4 enters inside. Now again 2 will be marked, and when we can make 2, 3, 4. Now the child of 2 has to be enqueued. Okay, so in this way it works. We are dequeuing every node one by one, and every time we have to check whether it is the goal or not. If it is the goal, we can stop the search, or we can search for more solutions also. So for every unvisited neighbor, we have to mark it as visited, we have to enqueue it, and we have to add the path one by one. So this is how the algorithm works. This is the pseudocode for our breadth first search algorithm. Now we can look an example. So we are going to apply the same graph. So this is a graph. It is an undirected graph. There is no directions kept over here. Directed graph will have directions like this. So here this is an undirected graph, and this is our starting node, and this is our goal state. Start state and goal state. So our aim is to reach from start state towards the goal state. We cannot go directly because in middle we have a lot of other vertices, we have a lot of edges. We need to travel different paths and we need to find the solution. So how we can find the solution and how the breadth first search works. Let us see that. So we have a queue. In the queue, first the starting node, we are keeping it. So our starting node is S. S is kept into the queue. When we make S into our visited set, we know that there are 4 children. 4 other nodes are connected to S. So what are the nodes? C, H, M, and J. These 4 nodes are connected. So as we are working with BFS, we know that 4 children are there. First, we should meet all these 4 children, and then we can go towards the child of the first node. So we are adding up these nodes C, H, J, and M into our queue. They will come into the visited when we are exploring the C, H, J, and M one by one. One thing I wish to make note of here. We have 4 nodes C, H, M, and J, but I have written it in the order C, H, J, and M. When more than 1 nodes are coming, we are going to follow the alphabetical order for exploring the nodes. So that's why it is mentioned like this. So now we can find that first node that we visited is S. The second node is C. Third node is H. Fourth node is J. And fifth node is M. How shall we move to the next level? We know our graph, we had 4 children. This is my starting node, and my first I have visited is C. So now the next level, this level is over. So now we are moving towards the next level. So first we should try to explore the children of C, next children of H, next children of J, and finally we should explore the children of M. When this level is over, we can move to the next level. So this is how the BFS works. So we are trying to explore the children of C. C is connected to 3, A, D, and H. But H is already in our list. So we can ignore this path. So we are getting these 2. That is, A can be marked as the 6th node that enters into the queue or the visited list. And D will be the 7th node which enters into the queue. So now we are adding them into the visited list. So the visited list will have S, C, H, J, M, A, and D. Now, which has to be visited next? Which node is being explored next? We can find that H will be explored next. So when H is being explored, already C and D are in the visited list, S is in the visited list, M is in the visited list. The only node that we can explore is F. So F is being explored. Next, the node J has to be explored. So J is having connection with 1, 2, 3, 4, 5 different vertices are getting connected with J. Among that, S is already visited. So all the other 4, we can explore them now. I, K, P and O. But we have to write it in the order I, K, O and P. Okay, so these are the next level of visit. And what comes next? The next, it has to explore. Now these are all marked as visited. We have to explore M. M is connected with H, S and O. So all the 3 are already in the visited list. We can ignore it and we can move to the third level. Now our second level is over. We are moving towards the third level. So now how our tree comes, we can see that once. S is the parent node. 4 children were there. C, H, J and M. So these are the 4 children. And C connected with A and D, as well as H connected us with F. J connected us with 4 different nodes, and M did not connect us with anything. So this is how the graph which we got. And now we are going to the next level. We are trying to explore A. A is being explored and B is the only node which can be connected to A. So we can see that B is the next visited node. So what comes next? When we see next D has to be explored, next F has to be explored. So D is being explored and all are already visited. So we are ignoring that. We are trying to explore it. So F is being explored, L is there, we are moving to L. L is now marked as visited. The next node that we are exploring is I. When I is explored, I is connected with J, K and E. J and K are already in the visited list, so we are going to mark E as the visited one. The next node that we explore is O. O is connected with M, J, P and R. Already these 3 are in visited list, so we are adding up R into our list. And the next one that we can do is with L. We are exploring L. And L is connected with F, N and G. So now we can mark this and finally we are reaching the goal G. So this is the final graph. These are all the vertices which we have visited on the way of tracking from our source to our destination. Just we had to move from here to here. But we have visited all these vertices. Many nodes are being crossed on the path. So finally we reached our goal. How to find the path from S to G? So here we can see that this is a path from S to G. From S we are moving to H, to F, to L and finally to G. So this is the path we got. But how did we get this path? We can see that a lot of edges are visited on the way to reach this G. Then how did we get this? So in order to show you that, I can show this tree structure for you. This is the same thing that we worked. We started from S. 4 children were there. They are written in the alphabetical order. After visiting that complete level, we are next moving to the first child C. We are visiting A and D, and then H we explored. So this exploration we did, and how we can write this path. Finally we found the goal, and from the goal we have to track back towards the route. How we reached from source to goal, we have to track it, the path from the goal towards the source. From goal's parent is L. The L's parent is F. F's parent is H and H parent is S. This is how we are getting the path as S, H, F, L and G. And how can we write the cost, path cost? How can we mention the path cost? We will get 16 plus 16 plus 6 plus 4. This is how we will calculate the path cost. So here we can see we have visited all these nodes and the path found is this, and the total cost is 42. So with this we can conclude the BFS, and the properties of BFS we can see completeness, it is there if B is finite. What is this B? This B is called as the branching factor. That is how many children can be there, maximum. To the maximum, how many children can be there. For this graph, the branching factor is 4 because the maximum number of children that a node has is 4. So if this is finite, in some of the graphs it will be infinite. In that case, we cannot get the completeness. And time complexity, how can we calculate? It depends upon the branching factor, because there are number of levels. The number of levels will be d. How many levels are there? The depth, it will be d. And we can see that here the time complexity for exploring this is 0. The branching factor, power 0. And the branching factor for the next level, we will get it as b power 1, b power 2. Okay. So in that way, we will get the branching factor as big O of b power d plus 1, where b is the branching factor and d is the depth of the tree. Space complexity is very similar to that of the branching factor, because every single node we have to save in the memory. In order to find out the path back towards the parent, we have to save it back. So the space complexity is same as the branching factor. And whether it is optimal? It is optimal if the cost of every travel is 1. It will not be optimal if the cost is different. Okay, so this is the final thing about the best first search. Now let us see the coding part for implementing this breadth first search. So here we can see it is implemented. So this part, it is showing the same graphical representation. So we can find that A and B are connected. So this part, it means that A and B are connected and the distance between A and B is 4. This is same taken from the graph which I have shown to you. And we are defining a final weight path, how to find the path. And the main part for defining this comes over here. So we are using two different data structures here. One is a set data structure. We are using it for maintaining the visited nodes in a memory space. And another data structure, we are using it a queue data structure. So we are calling it as D cube. It is nothing but a double-ended queue, that is insertion and deletion can be done at any one of the nodes. And an array is being used in order to maintain the order of visiting the nodes. And we can find that the queue is being popped out. Pop is the operation which takes the elements out of the queue. So we will be having the queue and we are taking the element out. And why it is pop left? We can save the element back into the queue because it is a D queue. It is a double-ended queue. We are saving it back. In order to save the space, we are using this logic. And whenever the visited list is being verified, when we explore any node, we are checking whether it is in the visited list or not. If it is there, we can ignore it. That's what I have said. When we are exploring a node, 3 children are there, but among the 2 are already in the visited. We are ignoring that and we are moving to the next only one node which is not in the visited list. So that check is being done here. If it is not in the visited node, then we can add that node into the visited list and we are appending it in order. That is, we are using the alphabetical order I mentioned you. So we are appending the node into the list in an order. Now we are adding it, we are arranging it in order. Okay. And every node when we visit, we should check whether it is the goal state or not. So here we are checking if the node is equal to the goal node. If it is equal to the goal node, we have reached the destination. We found the solution. So we can return what path we have taken, which order we have gone, total path cast, everything we can return, we can close the function. If not, if that is not the goal node, what we have to do? We should explore every neighbor of that node. We are taking it, a node from the visited list. We are comparing it whether it is the goal node or not. If it is the goal node, we can stop the process. If not, we are finding out its neighbor, we are exploring all its neighbor. So all the neighbors are being explored and that is added up to the queue. We are enqueuing it, we are appending the element. Append is the operation which adds the element to the end of the list. So here we are adding it up and we are adding the elements into the list. The same function when we ran, we are getting the output. This is the same output which I have shown you there. From the tree structure that we have seen, we have found that all these nodes are visited one by one, and how it happened we have seen in the graph example. And we got the path with 5 different nodes. Among all the visited nodes, we selected only this as the path. That reason also we have seen we are tracking the path from the goal towards the root node by finding its parent one by one. And the total cost for traveling from the source to the destination goal point using breadth first search is 42. Now we can see the next algorithm, how it works and how it is being executed, what will be the path cost if we travel through that. Let us move to the next algorithm, the depth first search. So this depth first search is also a graph traversal algorithm. The only difference is it will go deep and deep rather than going in zigzag and completing level by level. It is not using the level by level. It will go in deep. When it explores a node, it will not look who his neighbor is. It will again explore its child, and it will move deep and deep. So we have a start node. From the start node, we will find out the unvisited neighbor in depth order and until we reaches the goal. So when we reach the goal, we can stop it. So how this works? It always expands one of the nodes in the deepest level. So this is the depth of the tree. We can tell that this is in level 0, level 1, level 2, level 3, level 4, level 5 and level 6. The total depth of the tree is 6. So maximum we will try to find out the element which is there in the deepest nodes. So here we are starting from S and here we are mentioning it as G. Actually, this is being built from a graph, so we can find that many nodes are being repeated. It means that S is connected to D and again S is connected to A, and this A we can also find over here. S is also directly connected to A. So we'll have a graphical structure with all the connected nodes we are mentioning this graph. So if suppose we are trying to find out G, we are trying to find out the vertex G. We are starting from S. S is having 2 children. If this happens in the case of breadth first search, we will visit A, D. Then we will go for next level. It's not happening here. We are going to A. We are exploring the first node. And again, we are going in deep. Next level, we will go to its first child. To its first child, we are trying, it is an endpoint. Endpoint in the sense, it is a leaf node. C is a leaf node. We cannot travel more from C. So we have to come back to the previous parent node of C. This coming back and moving again is called as backtracking. So backtracking is applied in the case of depth first search. So we are coming back and from B we are going to the next node and there it has 2 children. We will explore the first child. Again it is a dead end. And how can we find that it is dead end and we don't have anything to move from there? Before that, we will check whether that is the goal node or not. It is not the goal node. Again, it is dead end. There is no more adjacent vertices to that. So we are coming back and then we'll move to F. We'll find G. Okay, this is how the depth first search works. So here we are applying the concept of backtracking search also. Where we are using this, we can explore as far as possible before backtracking. Before coming back, we'll try our level best to move down. So once we move down to the dead end, we'll backtrack. So before backtracking, we can try our level best. We can use this to analyze the structure of the graph. That is, whether any cycles are there. Cycles in the sense, if we have 4 nodes, and if this is there, and arrows are also there, we can tell that this part is forming a cyclic structure. If cycle is there, we will lose path over there. We will be circulating again and again over there. So that has to be avoided. To check whether the graph has a cycle or not, we can use this depth first search to find whether the graph is connected. What are the components? All these things we can use the depth first search to analyze the structure of the graph. We can use it for solving puzzles as well as research problems also. Also, we can work with trees as well as directed acyclic graphs. So these are the uses of depth first search. Next, let us see the pseudocode of this depth first search. In breadth first search, we have used a queue. In depth first search, we'll be using a stack. We are going to use a stack. The first point will be kept into the stack and immediately the pop operation should happen. So we will take the starting node outside. When we take it, its one child will be put into the stack. That child will be taken out. This is how the depth first search works. So first we can create an empty stack. We can push the start node into that empty stack. We have to create an empty set. One set also we are creating. Two different data structures we are applying here. And this set we are using to keep track of the visited nodes. Which nodes are visited? To check that we are keeping this. Okay. And now we are popping out the first element. We have to put that element into the set and its child will be explored. That will be put into the stack. So this stack area will hold one element to put and take it out, and that taken elements are stored in the visited set to track that which nodes are being already visited. So if the node is already not visited, we can mark it as visited, and this is very important. In every stage we should check whether that goal node has been reached. If it has reached, we can return the path as the solution path. If not, we should explore its neighbor and move one by one. So how long should we do this? Suppose if we are looking for an element, for a path, there is no path existing from that source to that destination. There is no path. Then in that case also we should get a solution that there is no path. How to get that? Until the stack becomes empty, we should push the elements into the stack and we can pop them one by one. If we are not finding any solution, we are not finding the goal node till the end and our stack is empty, we can stop the algorithm and we can tell that there is no path found. Same example we can start working with. We are starting with the same starting node and our aim is to reach the goal state G, and there is no other changes. We are going to do with the same thing. So S has 4 children, C, H, M and J. In the case of depth first search, it visited all the 4, but now we will go for its only one child. We will explore its first child. Its first child is C. We are moving towards C. So now it has 4 children, but we will visit only its first child. So C is being explored. Now again we have to move to its next depth. So we can see that S was there, 4 children were there, but we visited only C and we are trying to explore C. So C has 3 children, A, D and H. We have to keep note of one thing. All the 3 can be drawn here. Even though H is already here, we can have H over here because this H is not yet visited. Only C is visited. So in our visited list, H is not there. So even though it is there in that level for our reference, we can add it over here. So C's children are A, D and H. Among that, in alphabetical order, it will arrange. So A, D and H are there, but we will explore only A. We will select this A as our next child. So 4 are there, but the next selected part is A. Now the children of A we have to consider. So from A, we do have B, D and C, but C is already visited, so we can ignore that path. B and D are there. Among this, in alphabetical order, we have to choose B. So B is being selected. From B, we have A and F. A is already visited, so we can move to F. F will be visited, and F has multiple options, D, H, L. So here B is already visited, we can ignore this path, and D, H and L are all in the unvisited list. So here D wins the chance. So D is being visited. From D, we have A, C, F, H. Only H is not visited. All others are visited. So next, the option will be H. We are moving to H. H is being visited. From H, again, we'll move to M. M is visited. And from M, we can see H, S and O, but these two are already in the visited list, so we will move to O. O is being visited. From O, we do have R, M, J and P. So M is visited, so ignore it. J, P and R, which is the first one. If we arrange them in alphabetical order, J comes. So J will win the chance. From J, again, similarly, we are moving to I, then to E, moving to K, moving to P. At this point, we can see that when we are trying to explore P, J, K and O are its children. All these three are already visited. All these three are in our visited list. So there is a dead end. So this is how we can find the dead ends. We don't have any more place to move on. So when we are trying, we are going for a backtracking. So we are coming back, all visited. These are all visited until we reach O. All the nodes are visited. We are coming back to O. So again, we are trying to find whether there is another child for O. O had 3 children when we visited it at first time, J, P and R. At that time, we went through J. Now we can see P is also another child, but P is also in the visited list. We have to ignore it. So the only option is to move towards R. From O, we are moving to R. And from R, we have Q and G. So there, G is the first child according to alphabetical order. We are moving to G. G is the goal node. So we are getting the path S, C, A, B, F, D, H, M, O, R and G. This is how we are getting the path in depth first search. Okay. So if we show it with a tree diagram, we started with S, we explored it first child, then when we explored F, we went along all these directions, we moved back and finally we got into the goal. So we can see that here in this output, we can find the cost is 82. The visited nodes are more. Yet from a point from O till this P, we went for a backtracking. That's why in the path, those nodes are not coming. There O is getting repeated and we are getting this less path. What are the properties of DFS? We can see the 4 properties of normal search algorithms. The first property, completeness. No. It fails if the graph is infinite depth. Okay, the depth is infinite, it fails. But in some cases, the states can be modified and we can complete in finite spaces also. Then regarding the time complexity, it is taking big O of its branching factor power M. M is the depth, maximum depth of the tree. That's what we said. If the maximum depth is infinite, then completeness will not be there. We cannot find the solution. Because until it is going on, we will not come back to some other search areas. So as it is going deeper and deeper, we may fail. Completeness may not be there. And space complexity is big O of B into M, where B is the branching factor and M is the maximum depth of the tree. And whether it is optimal, no, it is not optimal. Now let us see the coding part of this depth first search. So in depth first search, we can say the same graph representation, the connection between the vertices, the edge cost is being given in this list of tuples. And we are initializing the graph. And this is the main part where we can see how the graph works. We are using a stack. In that BFS we used a queue. Here we are using a stack, and the visiting order, one set, 2 data structures we are using here. So when there is an element in the stack, so until the stack becomes empty, we have to check. So while there is an element in the stack, every time we have to pop the element, we have to add that into the visited list. If that node is not in the visited list, we have to add it. Then we have to check whether that node is the goal node. If it is the goal node, we can return the path and we can close the algorithm. If it is not the ending path, then for every neighbor, we have to add it into the stack, and we should repeat the same process again and again. So until the stack becomes empty, we have to go for the search. So if the stack is empty, we can tell element is not found, path is not found, we can close the search. If not, we have to move on, and we can tell that the element is found with this path. We can return the element's path. So here we can see what is the path found and what is the total cost. The total cost is 82. We are getting a total cost of 82 when we come towards the breadth first search. Now let's move to the informed or heuristic search algorithm. So two different algorithms we are going to deal here. One is greedy best first search algorithm, and another one is A-star algorithm. Some of the important terms, that is, we can tell it is the prerequisite, important terms that we should know here in order to work on this. We should know about f of n, g of n, h of n, Manhattan distance, and Euclidean distance. G of n, suppose you consider two nodes are there, it is getting connected, and this is my start node and this is my goal node. There is an intermediate node called A in between the start node and goal node. So this node will have some information, some additional information, how to reach the goal node. That we are calling it as the heuristic value. That we call it as h of n. Every node will have some additional information, how to reach the goal node. That information we call it as the heuristic value. So that comes in our h of n. And g of n is the time taken or the cost which has been taken to reach till this node from the source node. We may consider that in between many nodes can be there. So from source node to this node, how much cost has already been taken, that is g of n, and this particular node where I am now, it will give me an additional information about the reaching point. So that is h of n. So adding up my g of n plus h of n, we will call it as f of n. So these are the three things that we should know about f of n, g of n, and h of n. We will work this in our algorithm. And regarding the Manhattan distance and Euclidean distance, so this is used for getting the additional information about the goal. So how we can get it? For example, let us consider in a graph, this is one point and this is another point. Okay, so this is my start node and this is my goal node. Let it be anything. Okay, so how to calculate the distance between these two? One way is to find out the distance between these 2 points by using the common Euclidean distance. We will mention this point with x1, y1, x2, y2. So this Euclidean distance we used to get with the common formula x2 minus x1 the whole square plus y2 minus y1 the whole square. So using this we can get the distance between these 2 points. So this is called as Euclidean distance. How we can apply in Manhattan distance? The same graph, let us consider this is one point and this is another point. So this distance we need, but in most of the developed countries and all, we can find that the streets are in straight lines. So in those cases, Manhattan distance will work than Euclidean distance. That's why some algorithms we will be applying the Manhattan distance. So the Manhattan distance will give us the distance in this way. That is, here also we do have x and y points, but we will try to find the distance in this direction. The same we will apply in the grid. You will be understanding when we are moving towards that. So now let's move to the first informed, uninformed search algorithms are over. We are moving towards the informed search algorithm. The first one is greedy best first search. So this is a heuristic search algorithm because the additional information we are going to use, that additional information will tell how far the goal point is from my intermediate point. So that is the heuristic function. And this is called as greedy because the step by step when it moves, it is always greedy that to reach the nearest one, to find out whether it is the goal is very in shortest distance or not. It will go level by level in a greedy manner. So it is called as greedy. And mostly it does not guarantee optimal solution, but it is faster when compared to other heuristic search algorithms. It is faster than A-star algorithms. In our pseudocode, we can find that here we are going to use two data structures. One is a set, another is a priority queue. So the set is used for noting down the visited vertices, which vertex is being already visited. To note down that, we are using the set. And the priority queue, it uses the NQ and DQ operations as usual, but we will prioritize which element to be DQ'd. That's why we use it as a priority queue. So here, until the PQ is empty, we can find that the priority queue name is PQ. So we are enqueuing everything. Whenever we are exploring something, we are enqueuing that into our queue. So until it becomes empty, we have to go one by one. We should find which among the neighbor is having smallest heuristic value, which means that which node will take me to the goal with the shortest distance. So we cannot assure that that is the actual shortest information that has, but we will make a guess and we will make a move. So if the goal is being reached, we can return to the path. Otherwise, we can expand next nodes, neighboring nodes one by one. We will calculate its heuristic value and insert the element into our queue. We will move on. If suppose PQ becomes empty, until then we couldn't find the goal point, then we can tell that there is no solution. We'll complete it with either a solution or without a solution. What are the uses? This is faster. And search space is very large. This is one of the disadvantage. But if our heuristic value is very approximate, if it is a very good heuristic value, then we will get the solutions very faster. Now let's move with the same example. And here the heuristic value table is given. This is not given. This is extracted from our graph by using the Manhattan distance. This distance is calculated from the goal point, how much distance, how much Manhattan distance each node has. For example, let us consider node A. Okay, so from G, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's how the value, the heuristic value of A is 9. I hope similarly you can know. You can calculate how the heuristic values of all the nodes are calculated. We have to note one point here. The heuristic value of G is 0 because G to G is 0. So these heuristic values we are going to use when we are applying this heuristic function values in our graph. So we are starting from the same start point and our end point is G. How we can move step by step. When we start from S, we can find that. And one thing I have to make it clear, we are not going to consider how long we traveled till now. We are going to consider only from my point, how long it takes to reach the goal. That is, I will not use G of N in greedy best first search. I will use only H of N. So my F of N will be only H of N. I will not be using the G of N in this greedy best first search. So we will be starting from S. So I will compare the heuristic values of C, H, M and J. They are the 4 nodes. What is the heuristic value of C? It is 13. The heuristic value of H, it is 9. The heuristic value of M, it is 6. And heuristic value of J, it is 11. Among these 4, M wins because the value of M is the smaller. It means that if I go to M, there is a possibility to reach the goal faster. So I will select M. So we can find that M is being selected. And from M, now in my visited list, I have S and M. So from M, where can I move? From M, we have H, S and O, but S is already in the visited list. We can ignore it. That condition we are checking in our pseudocode. If it is already in the visited list, we have to ignore. So from M, now we are trying to move towards H or O. Again, check the value of H and O. Among this, O wins because the value of O is 6. So as a next option, we are choosing O. O is being chosen. Now from O, again we have J, P and R. So we should check J, P and R. The value of R wins. So next move will make it to R. From R, we do have G and Q. So G and Q are being checked. G is 0, so automatically we will select G. So these are all the vertices that we have visited. We visited only few vertices. We explored only a few paths. We reached the goal within some node visits. And we can calculate the path cost. It is 16 plus 8 plus 10. So this is the path cost that takes to reach from S to G if we are using the best first search, the greedy best first search. The same is shown in the diagram. So here this shows the tree structure, tree space structure. So 4 children are there. M is having the less heuristic value, so we selected M. M had 2 options. O is having the less heuristic value, we selected O. O is having 3 options. R is having the smallest heuristic value 4, so we opted 4 and we went to R. From R, we had 2 options, G and Q. G is with heuristic value 0, which is less when compared to Q, so we opted that. How will we write the path? The path will be S, M, O, R and G. So the path cost will be 50. Even though our visited elements are very less, our path cost is more when compared to the previous 2. And we found a solution, we stopped. It doesn't mean that that is the only solution. There are different solutions too. We can tell that the solution which is being found by this best greedy first search is not an optimal solution. We got 2 other solutions which has less path cost. Now let's see the properties of greedy. Whether it is complete? No, there is a possibility to get stuck in the loops if there are cycles in the graph. Is it optimal? For sure. Even in this example, we did not get an optimal solution. No. And time complexity of it, it is the branching factor power m. And the space complexity is also the same. When we are using only the h of n heuristic value. We are not using the travel time which we took from the source till that point. And let us see the program for this greedy best first search. The same graph we are applying. The important thing that we have to add here is we should add the heuristic values that has to be saved, which will be used as an input. 2 different data structures we are applying here, a set and a priority queue. So the elements one by one we are going to enter. So until the queue is not empty, we are getting the elements one by one. We are checking whether that node is in the visited list. If it is in the visited list, we can ignore and move on. If it is not, suppose if we don't add this line, what happens, even if it is in the visited list, we will visit it again and we will get into a loop. In order to avoid the loop, in order to not to waste the time and space complexities, to avoid that, we are adding these lines over there. So when every node is being opened, we will check whether the node is the goal node. If it is the goal node, we can stop. If it is not the goal node, again, its neighbor has to be added up one by one into the path. So when we finally get the result, we can see that the visited nodes are 5 nodes, the same as the path, and the travel cost is 50. So this is what we are getting for greedy best first search. Let us move to the last heuristic search algorithm, A-star algorithm. This A-star algorithm is an informed search algorithm or heuristic search algorithm because we are going to use the additional information which is given by every node, which gives the information about reaching the destination. So the actual cost will be using G of n. We will be using H of n, and this is the important formula that we have to apply in the case of A-star algorithms, because we'll start from, let's think that this is our starting node, this is our goal node. This is some intermediate node. In between many nodes we have crossed. So this node will give us a h of n value which tells how much distance it takes to reach the goal. And here we will have an g of n value which tells from the starting node how much it took to reach this particular intermediate node. We will add up these two in order to make a move towards the next one. So those values are being applied in the case of A star algorithm. Let's see the pseudocode of this. Here we are keeping an open list. Initially that open list will be empty. This is for finding out the visited vertices. And one by one we will be removing, and this open list will be a priority queue. Again we are using the priority queue because here we'll use g of n plus h of n, which is our f of n. We should find the minimum value of f of n that has to be prioritized. So we are using a priority queue. So every node, again, we will check whether it is the goal node. If it is not the goal node, we should try to make it, add it into the visited list. We should expand it. We should try to find what are its f of n values of the neighbors. The minimum value, again, we will move and we'll try to explore it. So this is how we are moving. Suppose till the end we couldn't find the path and our priority queue is empty. All nodes are visited, yet we couldn't find a path. Then we have to close it telling that there is no path from source to destination. So the advantages of this is here we can get the optimal path. One thing is heuristic value which we use should be admissible. Almost approximate values if we use, then it will give a good result. So there are many variations of this A star algorithm which tries to make the heuristic values admissible. So if it is admissible, then we will get the optimal path. That is the best shortest path we will get. And this is combining the advantages of both the greedy search as well as the uniform cost search algorithms. So it reduces the search space if heuristic value is good. And some of the disadvantages are, if our heuristic value is not that good, then we might visit all the vertices and this will take much space occupancy in the memory. And if pure heuristics are there, then this will be slow. These are disadvantages. So the only thing that we should consider when we are going with applying the A star algorithm is the heuristic value should be admissible. Then we will get better solutions. We'll start with the same algorithm. The same heuristic values are used. For example, let us consider M. How this M value, we got it as 6. M is 1, 2, 3, 4, 5, 6 Manhattan distance from the goal state. That's why we got this M value as 6. The same values are being filled. Manhattan distance values are filled in our heuristic table. That is the heuristic values that we consider. It is little complicated when we work with this A star algorithm. Now let's see that one by one. So we are starting from S and our goal node is G. We are having 4 different options to move towards the next node C, H, M and J. 4 options are there. And now we should find out the minimum value of f of n, not h of n. We applied h of n, minimum h of n we have calculated in greedy best first. But in this case, we should find out the minimum f of n value. So what is the f of n value of C? How can we calculate that? It is the distance from S to C is the g of n for that node. So 6 plus, what is the heuristic value of C? It is 13. So this is how we have to calculate the f of n value for each node. So what it comes for H? For H, it will be 16 plus 9. For M, it will be 16 plus 6. And for J, it will be 11 plus 6. So we have to compare these 4 and then we are finding that J is having the less f of n value. So J is selected. And now from J, it has S, O, P, K, I. 5 different options are there. 5 nodes are connected to it. But S is already in the visited list. So ignore that path. The other 4 paths we have to consider. So we should consider towards I. J towards I, it is 24 plus this I value, 11. and j to k, 24 plus the k value is 14. Okay, so in this manner, we have to expand its 4 paths. So there we are finalizing that these values are more than the value which we calculated for C. In previous, we calculated the value for C as 19. Here we are getting 4 different values. These 4 values are greater than the value of C, that is 19. So we are opting C. Okay, let me show you the graph for this. Let us start with this tree structure. We are starting from the node S. So S has 4 children, C, H, J and M. So we are calculating the F values for these 4 nodes. How will we calculate the F value? It is the combination of G value and H value. The H values we are getting from the table, and the G values, it is the cost from the source towards that node. So now it is 6 plus, for C it will be 6 plus the C value, it is 13. We are getting 19. So in this way, we are calculating the F values for all the 4 nodes. We are using a priority queue. This should be kept in mind. If we are using a priority queue, the value with less F value will be there in the DQ end. That node will be visited next. So now among these 4 values, 17 is the minimum. So J is being visited. So let me mark the visited nodes. S is visited. Now J is visited because among these 4 values, 17 is the minimum, J is being visited and J is being explored. J has 4 different children and their F values are 44, 45, 22 and 41. Now we have to keep in mind that we should not try to explore only these 4 vertices. In our priority queue, already M is there with 22, H is there with 25, C is there with 19. So when we have 4 plus 3, 7 elements in our priority queue, the minimum element with the minimum F value will be prioritized. It will be in the DQ end. So now C will be DQ'd, which is having the F value as 19. So when C is explored, again 3 children it has, its values are 31, 21 and 21. Now in our priority queue we have H with 25, M with 22, A with 31, D with 21, H with 21, I with 45, K with 44, O with 22 and P with 41. So who is having the minimum value? We do have 2 options, D and H. How to select between these 2? We'll go with alphabetical order. So now D is selected and D is explored. Now when we explore D, we have A, F and H with 41, 22 and 27. Again, in the complete list, H with 21 is having the less value. How it is being explored, we'll number it. It is the first visit, second visit, third visit, fourth we have visited D and fifth we are visiting H. Now when we explore H, we are getting the values 27, 34 and 22. Let's see that who are having the minimum values. F with 22, M with 22, O with 22 and M with 22. So let's explore the value with alphabetical order. We will be exploring the node F. F will be visited as the 6th node. Now again when we are exploring, we are getting B and L with 34 and 24. Again we can tell that 22 is the minimum value and we are trying to explore M. Now M is explored, we are getting only O, that is with value 38. So again we have 2 O's, one with 38 and one with 22. Let us try to explore O with 22. So we are getting these 3 options. Again the values are more. So in the complete list, again we can find that this L is having the minimum value and now we are trying to explore L. When we are exploring L, we are getting G with 26 and N with 32. Also when exploring, we should keep in mind while every exploration, we have to check whether that is the goal node. Now we are finding out our goal node, we can end our search. So we can see that we have visited all these nodes, but our path found is SC. Our path found is we have to move towards its parent. Okay. From the goal towards its parent, we have to move. So our path found is S, C, D, F, L, G. We are getting the path and the total travel cost is 26. So comparatively, we can tell that this is an optimal solution. We can manually check whether there is any solution in this graph. Okay, so this is our graph. We can find whether there is any other solutions which will give you less path cost. We will not get any solutions in that manner. So we can come to a conclusion now. We are finding out whether this is complete. Yes, it is complete. And it will tell if there is a solution, and that will be an optimal solution. So it is always optimal when we use a very good heuristic value. And time complexity, it is usually big O of B power D. B is the branching factor and D is the depth of the tree. And space complexity, usually this has a very high space complexity. We have seen that unless we are moving towards the path, we are exploring a lot of things and we are saving them into our memory. And it is dependent on the heuristic value, and consistency is very good. If heuristic value is admissible, then we can tell that this algorithm, A star algorithm, is very optimal and very consistent to believe on. And now we can compare all the 4 different algorithms. So in DFS, we got the travel cost as 82. Now let us see the source code for our A star algorithm and how it is being implemented. The same graph we are using, the same edges, and this is a heuristic search algorithm. We should use the heuristic values. The heuristic values, by using the Manhattan distance, we have calculated that has to be loaded into our code. We are using SX for saving the visited nodes. We are using a priority queue because we know that we are adding up G of n and H of n into our F of n. That minimum F of n value has to be prioritized. So we are using a priority queue. And when this queue is empty, we can stop search. So until it is empty, we are searching it one by one. We are searching whether that node is not in the visited. In that case, we can append it to the existing list. We can compare it whether it is the goal node. If it is the goal node, we can stop because this is a heuristic search algorithm which is optimal. If we find the goal node, then that is the optimal solution to the maximum. And if not, for every node, we have to check the node. We should find the new G value, the old G value, plus the new G value, plus its weight, and its heuristic value has to be added with the G value, and we are getting the F value. Now, this F value is being compared by using the priority queue. The minimum F value element is again noted down. We can find out the results of this. The nodes visited, or a set of nodes we are visiting, but the path found, we are finally getting the path. We are backtracking from our goal node towards the parent root node. Total travel cost is 26. With this, we are concluding our A star algorithm. Let us have a comparison of all the 4 algorithms that we have seen. Our DFS, BFS, these 2 are uninformed search algorithms. We have got the travel cost of 82 and 42 in BFS. And greedy best first search and A star, these 2 are our heuristic search algorithms, informed search algorithms. So we got a total travel cost of 50 in BFS and a travel cost of 26, which is the optimal solution. But when we look at the graph, we can see that in A star, we have visited a lot of nodes. We are exploring a lot of things. Many calculations are done. Yet our travel cost is very less. So these kind of search algorithms plays main role in developing the AI systems. So when we are trying to find a solution, optimality is very important, and finding out Solution paths are also very important. All these things are being supported by the basic search algorithm. So this can be considered as a basic building block of an AI system. So with this, I am concluding. Thank you. Thank you all.